This is the graph of f of x equals 1 minus x over 2, g of x negative 1 plus x over 2, and x equals 0. And what we're going to do is actually treat this as a base of a solid. So we're going to have a three-dimensional figure coming out of the paper sitting on top of it. The cross sections for that solid will be the same shape from x equals 0 to x equals 2. So it could be that the cross sections are squares, equilateral triangles, semicircles, or something else. So if it was a square, you would start with a square with side length 2, which means it's going to come up 2 over 2 and back down 2. If I looked at a side length in here, it's obviously shorter because it's dependent upon the x value. This is negative 1 half x plus 1. This is the negative 1 plus 1 half x right here. So negative 1 plus x over 2. If it was a triangle, then this would be one side length of the triangle. The triangle would come up like this, and they would, of course, be smaller as the side length across gets smaller down to 0. So to find the volume of this solid, let's say that we're doing squares, then what we're going to do is actually integrate the area formula for squares, which is side squared. For all four of these solids that we're going to make, the cross sections are going to be perpendicular to the x-axis, so all of these are dx problems. If it was perpendicular to the y-axis, they would be coming out like this as a square, and it would be a dy problem. So for this one, the area formula for a square is side squared. So I know I'm going to integrate from my starting x value of 0 to my ending x value of 2. And I'm going to integrate a side length squared, and it's with respect to x. Now I know that the side length is the distance between these two lines, and you find that by finding the more positive function and subtracting the less positive function. So a negative 1 half x plus 1, and I'll subtract negative 1 plus x over 2. So plus 1 minus x over 2. I'm distributing the negative. You could simplify this down, square it, take the integral, but I'm more interested in setting them up right now. If we were doing equilateral triangles, I know that the area formula for an equilateral triangle is square root of 3 divided by 4 s squared. And you'll usually see coefficients pulled outside of the integral. So the square root of 3 out of 4 would be in the front. You're integrating from the same x values, 0 to 2. And your side length is the same. So it would be a negative 1 half x plus 1 minus x over 2, still squared with respect to x. If they were semicircles, I know the area of a semicircle is 1 half pi r squared. The 1 half pi gets usually written as pi over 2, and that's outside of our integral. We're still adding up semicircles from 0 to 2. It's the radius that's a little tricky. I'm going to square my radius. It's with respect to x. Then if you look at the figure, your semicircle is going to come up like this, which means if I do the more positive function minus the less positive function, that distance right there is not the radius. It's actually the diameter. The semicircle comes up and back down, comes up and back down. So whenever I do a semicircle, I'm going to do the more positive minus the less positive divide by 2 to get the radius. This divide by 2 is here because it's the semicircle, it's half a circle. So my more positive minus less positive, which you can also write as f minus g, f of x minus g of x, would be this expression right here. So this would give me the volume of a solid with a triangular base, this specific triangle with semicircle cross sections. For our last one, we're going to do rectangles that have a height 4 times the base. So I know that the area formula for a rectangle is base times height, but the height is 4 times the base. So my area equals b times 4b, which is 4b squared. The 4, the coefficient, would come outside of my integral. I'm still integrating from 0 to 2. My base would be squared, and this is with respect to x. So the base of my rectangle is the same thing as the side length of my square and the side length of my equilateral triangle and the diameter of my semicircle. So I could write it like I did up here. I could simplify these, or I could just say f of x minus g of x. It depends on what the specific problem is asking for.